Thanks. So in this talk, I'm going to start off with a little bit of the motivation as to why I was interested in looking at cortical layers across the cortex, which started with an MRI-based hypothesis. Then a little bit on how we do our layer segmentation, and now with deep learning on these 1D profiles. And then finally going back to those layers and looking at what drives MRI cortical thickness gradients cytoarchitectonically. So to start, we looked at patterns of cortical thickness in macaques and humans within sensory hierarchies. So this is the visual hierarchy. And on the top, you see the macaque, and on the bottom, you see the humans. And we were looking at how cortical thickness changes across the visual hierarchy, so V1, V2, V3. And so the left column is cortical thickness, the middle column is geodesic distance from V1, and the right column is visual hierarchy. And you can visually see that cortical thickness correlates with both geodesic distance and hierarchical position. And if we look at it more statistically, it's a very strong correlation. This is in the human visual hierarchy. As you ascend the hierarchy, the cortex gets thicker. The problem is that with MRI, while you can do very large numbers and show that this gradient is present in every human that you look at, the source of the signal is quite ambiguous. So does the regional change in cortical thickness arise as a myelin artifact, or is there in fact a change in cytoarchitectural thickness? And if there is it all layers that are changing, or is it only certain layers of the cortex? At the other end of the scale, you can use histology to be very specific about what's changing. You can segment all the cortical layers, but generally speaking, histology is done on a smaller number of samples with oblique cutting artifacts and things like this, which might stop you from being able to measure such a small, being sensitive to such a small change in cortical thickness. And just very briefly, the reason why we're interested in which layers is that different layers have different properties, neuronal, synaptic, myelination properties. And so if we can localize more specifically which layers our signals are from, that can be more biologically informative. In the interest of time, very briefly, we are reliant on classical atlases to date for our understanding of laminar cytoarchitecture. So, for example, the 1Dconvolutional atlas, where he's measured layers, depths, and densities, but only in a few areas, maybe 50 or 60 areas. Or the equivolumetric model from Bock, where he predicted the changes of position of layers based on curvature. So layer 4 is more superficial in gyri and deeper in sulci. The issue with both of these is, as I said, it's 2D and is quite a limited number of samples. So it would be nice to update these maps with higher density data sets. And so this is partly what the BigBrain was aiming at, which was to link some of the cytoarchitectural insights we can achieve with large-scale in vivo type analyses. And so the BigBrain was a post-mortem data set which was sectioned at 20 microns and then digitized and then reconstructed into 3D so that you end up with a 20 by 20 by 20 isotropic histological volume in which you can see laminar structure. So very briefly, what we did is we were extracting intensity profiles, creating tools to segment cortical layers on each of these profiles, and then automatically identify layers across the entire cortex, and then finally quantify the variation in laminar structure, both morphological and regional. Don't have very long, so I'm going to skip over this bit, which is just that we showed that the equivolumetric principle was present in the BigBrain across the entire cortex. I'm just going to focus on the 6-layered variability. So in order to segment all 6 layers across the cortex, we use deep learning, which is a set of machine learning tools that are commonly applied for image segmentation and classification. And the nice feature here is that if you give it some training data, it will learn features within cortical profiles that correspond to layer transitions. So rather than having to specifically say, I'm looking for a peak, which might be layer 4, it'll learn the types of things that look like layer 4 and be able to automatically apply them to the profiles that you give it. So here's the training data that we give it. We label different areas of the cortex. We have 45 to 50 segmented areas where we've gone to the high resolution histology and manually segmented out 6 cortical layers. We've co-registered this to the BigBrain volume, and then we start extracting intensity profiles from the peel surface down to the white matter surface. And so what we end up with is a intensity profile of the raw image, the 20 micron volume of the BigBrain. We have a smooth one to give it context, and then we have the ground truth segmentation, where we've told it which parts of each profile correspond to which cortical layer. So you can see the two profiles. So we've got the raw profile here, the smooth profile, and the ground truth segmentation, and again for another profile. And because they're 1D profiles, you can sample each of the training areas many, many thousands of times to create the kind of data set you need to train a neural network. So we train the network on all of these examples and then test it on the entirety of the BigBrain. And what you end up with is 3D reconstructions of the 6 cortical layers across the cortex. And so this is the original plane of section, the coronal section, in which the brain was sliced. But actually, you can see the 6 layers in any section that you choose, horizontal, sagittal, any oblique section. Just as if we zoom in a little bit on a couple of the training areas, you can see that within the training areas, the layers, which are the colored lines, follow the manually segmented layers. But outside of those training areas, they continue to follow the appropriate features. So it's able to learn things from the training sections and apply them to the test areas as well. If we zoom in on this particular area, this is the transition between V1 and V2. Most visible because of this very large change in layer 4. So the red and the yellow lines are the upper and lower bounds of layer 4, and you can see that just here there's a sharp transition from a very thick layer 4 to a very thin layer 4, and this is the transition between V1 and V2. What's really nice is that the network has internally learned to apply different sets of rules for V1 areas to V2 areas in order to give this thick layer 4 that we need in V1. Which means it's internally learning at least certain area classifications. Briefly, this is something we're exploring more explicitly in a poster here. This is work done with Hannah Spitzer from Jülich on the UBrain data. And here we're learning, rather than layer segmentations, we're learning area classifications. And what you can see is that, so the yellow lines are V1 and the blue lines are V2. And the network is able to learn very accurately which profiles correspond to V1 and which ones correspond to V2. If we go back now to the segmented layers that we have for the BigBrain, we can start exploring where those MRI gradients might come from. So the first thing is, if we first look at just overall total cortical thickness and check that the maps we're getting are plausible, we can see now that the motor strip is very thick. The numbers are a bit small on von Economo's measurement of the motor strip, but I assure you they are also very thick. And the occipital cortex is thin, and again, we're finding that in the BigBrain. What's nice is that maybe there's 50 to 100 points that von Economo measures, whereas we have upwards of 500,000 points now in the BigBrain that you can analyze. So if there are more subtle signals, you might be able to find them with this larger amount of data. So this was the MRI gradient that we were looking to verify in the cytoarchitecture. And if we map the same partialization scheme to the BigBrain surfaces, you see that the gradient is definitely there in the histology as well. So this is not a myelin artifact we were measuring. It's a histological thickness gradient. If you measure it both in terms of the visual hierarchy, or if you do it in total cortical thickness. If you do it from geodesic distance from V1, this gradient is very much present. What's nice is we can now say which layers are driving this total cortical thickness gradient. So we can compare each layer with the geodesic distance from V1. And what we find is that this overall total cortical thickness gradient is primarily driven by changes in layers 3, 5, and 6. And this is nice because it kind of matches with the single cell studies, because layers 3, 5, and 6 are the pyramidal neuron layers. And single cell studies of macaque pyramidal neurons show that the pyramidal neurons of layers 3 and 5, their arborizations increase quite a lot over the visual sensory hierarchy. So what we could hypothesize is that overall MRI thickness gradients are driven by mesoscale changes in layers 3, 5, and 6, which are in turn driven by microscale changes in the arborizations, the increasing volumes of these pyramidal neurons. So in summary, the BigBrain offers a way of novel cytoarchitectural insights and linking these to MRI. The 3D cortical layers can be used as models for MRI cortical analyses. And the tools that we're creating for 1D profile analyses could be used equally on 2D histology or myeloarchitecture or autoradioreceptor data, but also for MRI data, and even can be applied to non-cortical biomedical segmentation, such as fetal compartments during development of the cortex. So with that, I'd like to thank all the collaborators from Cambridge, all the team from ULISH, and collaborators in Montreal, and thank you for your attention. Any questions?